Yeah, in this session, we will try to look out for a partial proportional hazards model, wherein one of the most important models for estimating the future lifetime, estimating future lifetime, we are trying to use one of the more famous proportional hazards model, which is called as a Cox regression kind of a model. We'll try to look at what it means. But of course, before we get into it, we'll try to see what are the fully parametric kind of models for estimating the future lifetime. What major limitations do they carry? And what is the prime reason of getting into semi-parametric kind of models, where we call them where we use Cox regression and these kind of models. Typically the proportional hazards kind of models, they get classified as a semi-parametric kind of models. So using the semi-parametric models, how do we get into the estimation of the lifetimes, and how do we get into the maximum likelihood estimation approach? How do we define the various statistical properties, and all those aspects is what we would try to look up. So just to get started, when I talk about estimating the future lifetime, right? When I'm talking about estimating the future lifetime, we can use semi-parameter, or we can first we'll talk about using a fully parametric approaches. What are these fully parametric approaches? I assume that the future lifetime follows some distribution. I assume that the lifetime follows some kind of a distribution, like either an exponential distribution, or probably a Weibull distribution, or some such kind, or a logistic or log logistic kind of distribution. Some such kind of distribution is what I can assume that the future lifetime will follow. And once I assume it based on a comparison with the real world observations, right, based on the mapping with the real world observations, we will try to find out the parameters. Probably if I am saying exponential distribution, I know that yeah, it is of the form lambda e per minus lambda x, the probabilities. Now what I can do is I can find the mean, or probably when I say exponential distribution, I know the mean of it is 1 by lambda, the variance of it is 1 by lambda squared. So what I can think of doing is I'll try to map my real world data's mean with the exponential data mean, map the real world data's variance with the exponential data's variance, and probably try to create an exponential based model, and try to find out, or try to fiddle out with my lambda computation, and then try to fit in an exponential distribution for the future lifetime. But in real world, what could happen is, if the fitment is not that good, especially when we are talking about a lot of complexities involved with the real world data, the fitment may not be that good. So depending on the assumption of the model which we are making, whether it is exponential or Weibull or log logistic or log normal or whatever it is, depending on the model, depending on the distribution we are choosing, the entire the probability of survival or the survival function itself, it would be modeled completely wrongly, which means I cannot use it for any of my estimations or even for determining the premiums or any other stuff. So in some cases what could have happened is, probably if this is the exponential distribution I am trying to model, any value of lambda I am choosing may not be a good fitment to the real world at all. So I mean, assuming the underlying distribution and then going forward with it and estimating the parameters of the distribution from that underlying assumption in real worlds becomes slightly difficult. So, and that too, if my population, if my data is coming from various subgroups, gender wise difference, smoking status wise different, age wise difference, or risk characteristics wise difference, health status wise difference, probably you can think of each individual species may not be or a group of individuals may not be homogeneous in terms of all risk characteristics. So the difference in the risk characteristics is adding up to the uncertainty associated with the prediction of the survival function. So that is where a direct fully parametric models may have a lot of limitations when we are going with the estimation of the survival function. So that's where we are getting into a slightly different kind of an approach, wherein we are talking about the usage of covariates as a part of a semi-parametric kind of model, or I will be talking about the regression model soon. So we are talking about the usage of covariates. Probably I can talk about all the entries that differentiate people. Could be age, gender, health status or smoking status, right? Health condition, salary, or probably a weight. All these things, they could be the differentiators, and any differentiator about various people whom the data of which we will gather for the purpose of mortality investigation, we call them as covariates. So some of the covariates are more of continuous in nature, like probably the weight, the salary, they are more continuous in nature, or they could be categorical in nature. Let's say gender is categorical, smoking status is categorical, health condition is categorical, where we are talking about multiple values. Whenever we are talking about categorical, we are talking about multiple values associated with them. Probably when I'm talking about gender, I'm having values like male and female. So the way we take the coding as a part of the regression for them is, we'll directly take it as ones and zeros. Yes, we'll take a covariate Z1, which will have a value of 1 if it is male, 0 otherwise. Now, which means I don't need to consider for a female separately. But probably if I'm having, let's say, smoking status, where I want 3 statuses to be there, like heavy smoker, moderate smoker, light smoker. The way we carry them as a part of our covariates is, I'll take Z1 equal to 1 if the person is a heavy smoker, 0 otherwise. Similarly, Z2 equal to 1 if he is a moderate smoker, 0 otherwise. This is, and I don't need for Z3 anymore, because if both of them are 0, then I can directly take the person is a low smoker itself, low or no kind of a smoking status itself. So basically, if any particular category is having n possible values, I can create n minus 1 covariates, each having a value either 1 or 0, depending on whether it belongs to that group or does not belong to that group. Like in this example, if there are only two possible values like your gender, male and female, one covariate will solve the purpose. But if I am having three possible values for my category, then I need to have two categories, because both of them being 0 will take care of the third category altogether. So once we have identified the various covariates for our model, then we are trying to map, we are trying to fit a model using the regression. Using regression, we are trying to fit a hazard function, probably mu, which is a hazard function. I am trying to model based on the covariates. Okay, Z1, Z2, Z3. I can create probably beta 1, Z1, beta 2, Z2, beta 3, Z3. I can do some kind of a modeling of the hazard function with the various covariates that we have chosen, and this kind of a regression equation is what we are going to develop, and this forms one of the basis for our estimation of the hazard function. So wherein I am trying to take the various covariates. In some cases my covariates can still be pure continuous values like salary. There I am not doing any kind of codification for them. But if they are categorical values, I am doing a codification by giving them 1 or 0 kind of values. So let's say I am trying to model my hazard function or mortality, force of mortality using these various covariates. So basically what we can think of is using this covariates like this. When I am trying to estimate the mu, I should be able to compare the hazard function of two or more groups of data, because I am having two or more group, all they are not homogeneous category of values. So compare the hazard function of two or more groups. So say that probably whether a particular covariate has any kind of additional impact on the hazard compared to the other group. So in general form, when we talk about the proportional hazard, okay, here I have to introduce you to another piece called proportional hazard model, where we try to model the relationship in terms of some proportions. Like, okay, I am talking about the hazard rate at time t based on a set of covariates z. What we are saying is, I'll take the baseline hazard at time t, means no covariates present, all covariates are zeros, and I take this covariate as a function of z's. So what will happen is, if I am trying to see, when I am talking about this is a baseline, irrespective of whether this is something where all the covariates are 0, where the values of all the covariates are 0, whatever is the hazard that is present at time t, that is what we are taking as lambda naught of t, which is what we call as a baseline hazard. And this is what we are taking as the covariate vector, which can be estimated through the various approaches. So the hazard function is what is typically estimated through this kind of an approach. When all the values of the various covariates are 0, whatever is coming out, that is what we are calling as the baseline hazard function. And what is coming out is, let's say I am talking about two groups of people with two different sets of covariates altogether, I should be able to take their proportions, because this is lambda naught of t into g of z1, whereas the other one is lambda naught of t into g of z2. So basically it is coming out like the dependency, it can be modeled in a proportionate form, and the dependency is in the form of a proportion. So one is how much times that of the other. That is what is an advantage we can look out with the proportionate hazard model. We don't make it dependent on t. So the comparison between the hazard rates of various sets of coordinates can be done quite comfortably using this kind of a model. And more specifically, out of these regression models, one more appropriate model for our case is the Cox regression model. Just like the generalized form lambda t with z as covariate, we are talking about lambda naught of t. But here, instead of directly taking, some function of z, where various covariates, this clearly mentions take it as e raised to the power of z1, b1, beta 1, z1, beta 2, z2, so on. A vector of all the various covariates are taken as a part of e to the power. So we are talking about the various betas, right? And lambda naught again being the baseline hazard function. It is purely based on the time period t, and it does not depend on the covariates at all, especially when all the covariates are zeros. That is what will work out as a part of the baseline hazard. And what we are seeing here is this is what we call as a semi-parametric model. Why? Only some portion of it has parameters. Only this portion of it has parameters beta 1, beta 2, but this baseline hazard we don't have any kind of parameters. Right, so in the baseline hazard there are no parameters, only in this exponential function we are bringing in the parameters. So that's the reason we call it as Cox regression kind of a model, as a semi-parametric kind of a model. Now, the interesting thing comes with respect to the estimations of beta 1, beta 2, so on, whatever are the various parameters. So here we introduce what is called as partial log likelihood function, or probably we'll go with partial likelihood first, then we'll take the partial log likelihood and then try to do the estimation. What it says is, you consider, right, when I'm talking about the partial log likelihood function, let's say for estimating my beta here, I am talking about e power beta z divided by sigma e power beta z. What I am trying to specify here is, depending on the set of lives, that are at risk before the jth time. Here I am, if I say zj, and even here I'll take it as zi, where ri belongs to the rpj. What does that mean is, okay, let me consider the various lives that I am considering as a part of my risk analysis. Let's assume that I am considering 10 lives as a part of my risk analysis. Assume 7 of them are males, 3 of them are females. Now, assume, because this is a categorical variable, I'll create a covariate saying z1 equal to 1 means male, 0 means female. Now, for males, what would have been this expression? Lambda of t comma z if it had been a male, it would have become lambda naught of t e power beta 1. This would have been for male and for a female, this would have become lambda naught of t into, there is no e power because that one is 0. So for females, this would have become something like this. For male, this would have become something like this. Now, initially, let's say for the first male, right at the start, these are the likelihood functions for each one. So first consider the first death that has occurred. The first death that has occurred. Now, is it a male or a female? Let's say if it is the first death is a male. What I will take is the males, this function is what I will take. Lambda naught of t e power beta divided by the total of all these, right? When I'm looking at the initial thing, it is lambda naught of t into e power beta, but here when I'm looking at, okay, lambda naught of t, now for all of them if I am considering, right, for all of them if I am considering, for the 7 males, let's say 7 males are there and 3 females are there. For the 7 males, I will have this lambda naught of t into e power beta. So it becomes 7 e power beta. And for 3 females, it just becomes lambda naught of t. So what happens is my likelihood function associated with the first death actually becomes e power beta divided by 7 e power beta plus 3. This will be the likelihood function associated with the first death. The force of mortality, this is the force of mortality, lambda. The force of mortality for the life who has died divided by the total force of mortality for those who are alive before this person has died, which means include this person also as a part of the model. Now let's say after a few more days, the second death has occurred and the second death is a female. Now for a female, the hazard function is only 1. But what about one male has already died, so there are only 6 males that are left and 3 females. So the second for the second death, the hazard function will become 1 by 6 e power beta plus 3. Like that, whatever are the number of observed deaths that have come up, I will compute their likelihood functions, and during the observation period, whatever deaths have occurred, will take the multiplication of all of them, and that is what we call as our partial likelihood kind of a function, right? So probably now just to give a better example, okay, initially we had 10 people, 7 males, 3 females. Now during our observation period, first one male has died. First male died. So the contribution to the log likelihood, we know when we have modeled Z1 equal to 1 means male and equal to 0 means otherwise, which is female. So first male has died. So for males we know that our hazard function is lambda naught of t into e power beta, whereas for females it is only lambda naught of t. Now because the male has died, the died person's hazard function lambda naught of t e power beta divided by total all people's hazard function. There are 7 males, so for each one of them it is lambda naught of t into e power beta. So it becomes 7 lambda naught of t into e power beta, and there are 3 females, and for 3 of them it is lambda naught of t only is their hazard function. So overall what we are saying is if I take out the lambda naught of t, it becomes e power beta by 7 e power beta plus 3. Now let's say after some time we see a female has died. A second death is of a female. Now the same logic, the female's hazard function is lambda naught of t, right? So I'll remove that lambda naught of t 1 by, there are 6 males, so for each one of them 6 e power beta, plus there are still 3 females that are left, so 3. So the second proportion which I am taking is 1 by 6 e power beta plus 3. And after that suddenly let's say there are 2 people died. Suddenly there are 2 people died, one male and one female on the same day at the same time. So here, okay, the contribution of the male, let's say e power beta divided by, because both of them have died at the same time, I have to consider, okay, now there are 6 males plus only 2 females. Similarly, I'll take the female one also, 1 divided by, because both of them have died simultaneously, I will not disturb the denominator here. So, when there is a simultaneous death, we'll take it like this, multiply these e power beta and here take it as 6 e power beta plus 2 whole squared. So, this will form my log, this will form my partial likelihood function for the estimation of beta. Now after that I can find out the log likelihood for the same by taking the relevant logarithms. I can find out the log likelihood function. So first I can find out, okay, log e power beta, which is okay, beta minus log 7 e power beta plus 3. So here when I am taking the logarithm, log 1 is 0. So I will get minus log 6 e power beta plus 3. Then again I will get another plus beta minus, okay, log x squared, right, 2 into log 6 e power beta plus 2. Let's say this is what we are trying to get as the log likelihood function. Now all I can do is to find out the value of beta. I'll try to take the derivative 1 with respect to beta is what I'll take, 1 plus 1 minus 1 by 7 e power beta plus 3, right? This is how I'll take 1 by 7 e power beta plus 3, and for this it again comes out as 7 e power beta. Then again I'll take minus 1 by 6 e power beta plus 3, multiply it with 6 e power beta. Like this I will do the solving for the same, and finally I can find out the value of beta. Whatever the value of beta I am getting through this simplification process is what is my maximum likelihood estimator for beta, which is the coefficient associated with the covariate, which is the coefficient associated with the covariate z1 equal to 1 for a male, right? So that is how we get into the estimations. And what we typically see is once that beta is obtained, we are majorly constrained with respect to finding out the partial, finding out the asymptotic properties associated with that maximum likelihood estimator beta. But all we have to understand is, because this beta is a maximum likelihood estimator, it will generally follow a normal distribution with a mean of beta and the variance going with the Cramer-Rao lower bound rule, which talks about minus 1 by minus 1 by second derivative squared. Minus 1 by second derivative squared is what is the variance that could be directly be considered, and that is what will become an unbiased, I mean that is what will be the variance which will help us in trying to determine the standard deviation and probably 95% confidence intervals associated with the beta. So we should be able to solve the second level differentiation for this log likelihood function, substitute that value which will help us in deciding the variance associated with it, and based on that we can find out the standard deviation which will help us in identifying the 95% confidence interval associated with our predictor. Now one more thing we are trying to see is, okay, if at all I want to test the effect of whether the adding a covariate had any kind of impact on the hazard rate. For that, a straightforward formula is given to us, right? We can go ahead with a straightforward formula which talks about a test statistic which is take minus 2 times log likelihood of p minus log likelihood of without the covariates, with the covariates. Try to find out the log likelihood function without covariates minus the log likelihood function with the covariates, right? Depending on how many covariates we have added, take the log likelihood function without the covariates and with the covariate. Let's say I want to differentiate whether there is any difference in the hazard between males and females. See, for female, if I am taking Z1 equal to 1 means male and 0 means female, all that it means is in males there are 1 covariate, whereas for females there are 0 covariate, which means probably there is one additional covariate that is getting added. So what I would try to do is, without the covariate, without including this Z1, consider the log likelihood value. Considering even this L1, find out the log likelihood value. So compute minus 2 times log likelihood of LP minus log likelihood taking all the covariates also, and then compare this with a chi-square distribution with q degrees of freedom depending on how many covariates I am going to test. If this, so this is what is the comparison that typically happens. So if this computed value is greater than the sigma q squared, probably at 5% significance level, then I can very well reject the null hypothesis and say that the beta is significantly different from 0, which means there is an impact of that particular covariate on the hazard function. Otherwise, I don't have any kind of an evidence to say that there is an impact of that covariate on the hazard function. So that is one way we can go ahead making a conclusion regarding the covariates and the impact they create on the hazard function. So just to summarize, overall we have looked at the basic fully parametric models, the limitations they carry, then how do I use the covariates as a part of my regression model, and a special case of that, a Cox regression model where I am looking at it as a proportional hazard space, and how do I use the maximum likelihood estimation approach for finding out the parameters associated with this model, and finally setting out the asymptotic properties associated with the estimation of the parameters. And finally, we also have looked at, in case I want to compare the hazard rates based on the multiple covariates, how do I test out for the statistical significance and how do I use the likelihood ratio test to basically conclude whether the covariates are having any kind of impact on the on the uh, force of mortality, on the hazard rate or hazard function, or they don't have any kind of a significant impact. We'll anyhow take up a few numericals in this aspect to really try to link this conceptual things to the numericals and then try to get much more hold on this particular proportional hazards model. Alright, but conceptually if you find any kind of issues regarding the same, you can very well get back to me by giving me a call on the number that I have provided below, or you can send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.